Hey everyone, Rob here from Rising Edge Industries, and this video is going to be part two of a product overview. The first part was mechanical and interfacing, and this part is going to be mostly focused on some of the design drivers we had here when we were architecting and developing the product, and its features, some of its characteristics, functional parameters. So we'll start just by a quick description of this CAD of the unit. Check out part two for more details. But over here you can see there's two units, production form factor. This is a side view. This is a pack of playing cards, standard playing cards, and this is a top view of the unit. Tongues here, USB link, and so this can give you just kind of an idea of how large the unit is. Here's a side view of the cards, and so you can see side view versus side view here with the product and the pack of cards. Just to see how small it is, half of this thickness or height is the battery pack that's embedded in the unit. Here is the USB link, a Glen Eyre MWDM machined metal housing connector with screw locks here, threaded socket screws on the cable side, and mating sockets on the connector side. Over here is the CAD. Since you can't see quite as well the PCB tongues for general interfacing through the webcam as well, there's a CAD model over here. And so we went over this in part one. Check that out if you want to see more. This video is intended to discuss more of the operation, some of the benefits of this device, what's new, some of the improvements we were really looking to achieve during design. And so the easiest way to go through that is to probably touch on what's in the brochure here you can get off our website. There's a list of bullet points that cover the most basic top level functional characteristics of the product, what makes it special, and generally how does it work. So we'll go through that at a very high level now, just as a general product overview here in this video. And following videos from here will be detailed use cases, and there's a lot more of these to come. So check out the playlist for much more detailed videos of the device in use, operation, measuring from Endevco accelerometers, and all kinds of different triggering mechanisms. But for now, let's stick to the general topics here. The device is based on a non-volatile memory architecture. That was one of the single largest drivers of product development is data preservation during failures, which are common in extreme environments like high shock and other violent mechanical environments. So one of the core pillars of this technology is the entire system is based on non-volatile memory from pre-trigger, post-trigger, data acquisition storage, as well as user configuration parameters that are used to configure and control the device. The data rate falls out as a throughput divided by bandwidth, or a throughput or bandwidth divided by the channels used. So the user can configure the device in multiple channel modes, 1, 2, or 4 channel data acquisition. And the fewer channels you use, the higher the data rate you get. So what you're basically doing is you have one number, data rate or throughput, and that's divided by a channel count. So here is just a brief table. One channel, you get the max data rate of 500,000 samples per second. 2 channels, divide that in half, you get 250. So you have 2 channels running in parallel at 250K. 4 channels, you have 4 channels running in parallel at 125K. So if you do have a application and you don't need all 4 channels, you're not locked into running them because it's hard coded. You can drop this down to 1 channel and you get the absolute maximum data rate of half a megasample per second. The main interface for command and control is USB 2.0. It is full speed and that interface is supported physically through a Glen metal 9-pin micro D connector here. And there's also, as you can see in the webcam screenshot here, there is a mating custom cable with this mating connector on the end here, and you can see that plugged into the unit. We did this in the previous video as well. The unit powers up, let it run. So the LEDs are visible. This is the main USB link interface. There's a custom cable that comes along with the unit. With this, that's manufactured by Glen for us. And one of the benefits of this via this link is the whole unit is plug and play. There's no need for drivers installation. There's also no need for software installation. The software runs out of the root directory when unzipped, and there are no drivers for this. So if you are under strict IT policy for security reasons, there's no need for any installation for this. So customers can buy this, you plug it in, it enumerates, and the software will automatically find it. So this is a true plug and play device. The memory for this system is all based on non-volatile memory technology, which includes the configuration settings. So when this device is connected into the configuration application, which we'll go over in more detail in a different video, the configuration that you program into the device is stored non-volatile, and when the device is power cycled, reset, it powers up and auto configures itself, and that leads into some other topics of self-triggering and automatic triggering, which we'll see in future videos how that works in detail. Another problem we're trying to solve is the power system and batteries for these devices are generally user implemented or customer implemented, and we wanted to fix that. You can see this is the side view. This bottom half right here is the battery compartment. So now there's a battery pack that's embedded and potted built into the product, and as covered in the last video, we talked a little bit about the charge indication, but it's controlled and fully charged and managed in the product. So it's charged through this USB link. There's no need for any customer hardware modification. We want to eliminate the risk of customers having to modify the product in any way. We want this to be software command and control. So that was solved with an embedded battery pack, discrete hardware control management system. Real quick, we can pull up the configuration application, and you'll see that when connected, there's a fuel gauge for this device as well here. So this unit is dead, but it's at 1%. It's got to charge the entire pack. So I discharged this previously for some testing, but this fuel gauge will increasingly fill up. It's just a software gauge, and so you get a real-time view. You can see there's a little bit of green here now, and the blinking percent symbol shows that it's actively charging and communication is up and running and it's good. So the internal electronics will handle this. It just needs to be plugged in, and then you'll get this status from the software application here. So that's a little aside. We'll cover all that in future videos, but the power system was pretty important. The memory system was extremely important, and trying to eliminate the need for customers to buy product and then perform hardware modifications was also a large driver in this architecture. So that's a little bit of the backstory there with the power system. So it includes a 500 milliamp hour rechargeable battery, and it's rechargeable by the USB link. The core technology improvement here, really a lot of it revolves around the memory system. Pre-trigger memory and post-trigger memory is non-volatile. The post-trigger memory is 1 gigabit non-volatile memory space, and the memory array to the user just looks like one contiguous memory block. And so that was a big improvement, especially for any kind of damage in these extreme environments. Brownouts are common in some of this testing, where you have a brownout, your power system dips, and you lose all of your data. Whatever gets written to the memory array stays in the memory array, whether you lose your power system or not. As long as the memory array doesn't get physically damaged, it can pretty much almost always be retrieved. So where the unit could be damaged, which would be unfortunate, but the data in the unit should almost always be retrievable. The driver-free plug-and-play USB interface we touched on. This particular unit we we're working with here is DR500 4DE SH. The DR500 is max data rate. 4DE is the channel configuration for differential-ended channels, and SH is shock hardened. We also have a mixed mode, which is differential and single-ended, and we also have a single-ended version only. But in this video, we're just going to talk about the differential-ended. So most production is based on four differential-ended inputs, and that's mostly because it's generally used to record from 3-axis or 4-1-axis bridge type accelerometers, and those are always differential. So the next upgrade we're shooting for was 500,000 samples per second, single channel rate. This is a slight increase of data rate capabilities, and it's really just we want to provide more data for a better picture of the dynamics going on within the system of measurement here during testing. The battery pack is 500 milliamp hour battery pack. The A to D has a 12-bit resolution. The product, as we talked about in the last video, has quite a bit of LED status indication. And so you can see this is a charge and power system. This is any kind of issue that arises or failure mechanism. If an error occurs, then we have an error indication here. And then these three on this side are general user indication, and these are all active during general use, which you can see in this video. We have a live signal, system good and up and running, generally in idle state here, ready to go. A busy LED when the unit's under operation, and then this LED on the end indicates that the unit has or has not been triggered. So the basic indication is brought out to LEDs. These LEDs can also be run out through a bulkhead here to external test equipment, multimeters, to allow customers to still see the status real time on a test range or any test facility. Even if you don't have access to the device, this can all be run through a bulkhead out or through an umbilical out to the world outside of the closed system this may be embedded in. So you can still see clearly what's going on within the unit. Has it been triggered? Is it ready? If it was accidentally triggered, you want to know before you run your test, so you can rearm the unit. So all of that can be wired out through a bulkhead. There are adjustable offsets from 0 to 3.3. The unit can go from 0 to 3.3 with its DC offsets, all software controlled, and so this is controlled through the configuration application here. And I can probably turn this off. Let's see. So this will allow users to command and control the DC offsets. Let's see, and we can actually run this offset cal HUD heads-up display. When you do check the unit offset configuration, you get a real-time streaming data plot of what the channel's seeing and what the offset is set to. You can set a target offset in samples as 12 bits, so you have 0 to 4095. So right now we're 2000. So if we there's quite a bit that plays into this. This is discussed in detail in further videos, but just as an example, we can set channel 1. Okay, so set at the 300, it drops down basically to almost 0. We set it to 3000. So there's a gain applied here, all 100. So let's do that. There we go. When the gain is applied, this is very sensitive, and so see future videos to see the details of how to configure this when you have large gains. But 3000, ADC code 2000, we'll set to ADC code 2000, and we're right on the money. And so each channel has a plot. You can see it real time. You can set all this up. You can also see the internals of what's happening with the circuitry that controls all this, and relative codes. They're not particularly important for customers, but they are there just to maximize detail and transparency. You can also set a voltage level for the device to hit, and it will auto-tune itself to as close as it can to the voltage configured. So there's a great hands-off, software-controlled DC offset configuration interface for this product, and for us that was a big step forward compared to, again, customers having to perform hardware mods on a product. For this kind of industry, we just didn't think was acceptable. So this was a big requirement in product development and architecture, that your DC offset knob is not only full DC from 0 to ground, but it's also user software configurable in a very clear way, from ADC codes plotted on the left. These are samples coming in, and we want complete software control, so there's no hardware mods for the device at all. So that covers the basics of offset calibration and user configuration. We won't go into any more detail. See further videos for more information on this. Turn the webcam back on. So the next bullet point here in the product overview is low power shutdown mode. That we touched on in the previous video a little bit. There's a 2-pin header here. I loaded in. This is going to stay in house as an engineering unit, so I loaded a 2-pin header for easy use. This is pretty handy if you're using this in the lab. You can just put a header on the product, install a jumper, turn it off. So the on-off interface here is normally on, and when you short the power enable header out, it turns the unit off. It does still charge when plugged into USB. So in this mode, the unit is in an extremely low power state, and customers can remove these LEDs to further improve that. But right now, there's very little current draw on the battery pack, so a fully charged unit will last for quite a while. And when we uninstall this, it powers up in its normal mode. So if you do need to embed this in a closed system, or a system that goes to overnight storage or extended storage, you can install this jumper. This powers down pretty much the entire system, so there's very little current draw here. The main command and control interface that we touched on previously, right here, this USB 2.0 command and control interface, is based on a machined metal Glenair housing connector. They're micro D MWDM series, and the cable is also made by Glenair for us. It's same high quality connector housing. It's also potted and assembled by them. Goes through their full quality assurance through their production processes, and then gets shipped to us, and we just supply this with the unit. We worked with them to get this designed and manufactured, and we've been real happy with these cables. They've been very high quality so far. The next bullet, the external power input capability. So if you do have a extended run duration for this product, there's a header we touched on in the previous video. I'll refer to that to save time here. Part 1. discusses the mechanical and physical interface here. On the electrical side, it's 6.5 volts to 12 volts external power input capability. This overrides the battery, so you can install this in any system that can provide this as a power rail to the product and power the unit for as long as you need to. You can also permanently install the USB cable and run that through a bulkhead or a USB extension out to your terminal where you're running the software applications and have USB access power for as long as you'd need. So that the installation of that and the headers are touched on in the previous video, but there is a external power input that allows customers to power this with something other than the internal battery pack and something other than the USB interface. The normally on hardware for power enable, which is shown here, this 2-pin header here. There are no mechanical or electrical devices actually enabling the device. It's normally on, so we want the device up and running at all times to eliminate a failure in that path. And the disabling of the device is where the jumper comes in, and so it's a normally on device. You short out that interface to power it off, and having that normally on functionality helped us increase a little bit of reliability and eliminate some complexity in any kind of enable circuit within the product. Discrete USB command triggers. The triggering can be USB communication link driven, again through here, through this micro D. You can command the unit to trigger. There's also a discrete input here on the sensor header. That's a discrete high to low or low to high transition trigger. It's user configurable, and that can actually be seen in the user software here. Got a rising edge, falling edge for trigger settings. You can also see the device is charged to 3%. And so the third triggering mechanism is actually an internal trigger. So the device can trigger itself internally. And that's touched on in more detail. It's a little too much for this video, but the device can actively in real time monitor in burst mode the incoming samples up to the max data rate, and upon seeing a sample larger than a user-defined threshold, it will trigger itself. It will save the last 4 megabits of data from monitoring in pre-trigger memory, and it will transition to post-trigger memory. So this is really a way for a customer to set a input sample threshold, and when violated, it will transition to post-trigger memory. And this gives you a snapshot of what happened before the event in pre-trigger memory, what happened during and after the event in post-trigger memory. And when you download the CSV data file, you can see that you've got, depending on the data rate, a period of time before the trigger event from pre-trigger memory. So there's really 3 triggering mechanisms for the product, depending on customer applications. There are trigger delays that can be programmed from 0 to 50 seconds. The signal range across all 4 channels can span 0 to 3.3 volts, and for this product, the sensor bias voltage is 3.3 as well. So this data acquisition all falls in a biasing and magnitude range of around 3.3 volts. The form factor we touched on before. See part 1 of the mechanical and interfacing video for more detail there. And you can also see that here there's just real quick a pack of playing cards, side view and top view of the product. There's a battery status report we'll talk about in more detail once we go further into software and configuration and all of those things. 13 kilohertz analog low pass filters on all input channels to eliminate noise. Adjustable input gains from 1 to 100 volts per volt. So this is quite a bit of gain, and we'll talk more about how that affects other configuration parameters. such as DC offset, which we saw earlier. The gain when I initially opened the application was at 100, and it has a very big effect and produces a pretty huge swing within the channel when you're changing parameters. But you can gain up signals in the analog front end by quite a bit. The filter, the gain, the DC offset. One of the big keys here with this product is that all of the signal conditioning and control is done exclusively in the analog front end. So there is no post-processing, digital signal processing. We actually have all of the controls for this platform for signal conditioning done in the analog front end. And what that means that's really nice is that the analog signal presented to the ADC is already undergone low pass filtering, gain configuration, and DC offset configuration. So what you see in the CSV file is exactly what is presented to the ADC. It's exactly what's digitized and brought into the digital domain. There's no gain, offset, discrete computation applied to the signal after it's acquired. And so that's really nice because you get the entire analog signal spectrum presented to the ADC in the digitization. Doesn't apply any of the signal processing changes driven by these controls. So these controls go directly into the analog front end and affect analog circuitry that then presents a final filtered analog signal to the A to D. So that can be different. There are data acquisition products that do a lot of post-processing, and that could eliminate some information that's carried along in the analog waveform. This product was really designed to preserve as much information or all information in the continuous domain, and so all of these controls here are implemented in the analog front end, and they're all implemented in real time. So there's no information lost in the time or frequency domain here. The pre-trigger memory buffer is based on a 4 megabit non-volatile memory array that we put together, and this is really critical in burst mode. There's 3 operating modes now in this product. There's one shot, which is only post-trigger memory, and once the unit sees a trigger, it begins running and acquiring data, writing it to post-trigger memory. So your snapshot T0 is at the event of a trigger. There is no history of what happens before that trigger, and so that's our one-shot mode. Our burst mode is really where pre-trigger memory comes in, and it's really critical because pre-trigger memory allows you in this circular buffer, this 4 megabit circular buffer, to loop incoming data samples at any data rate the product supports, including the maximum data rates. It loops through a circular buffer of this pre-triggered memory until it sees a threshold violation. For example, say the user sets a input sample threshold in ADC codes of 2000. So if you get a data sample that's over an ADC code of 2000, you want to save that pre-trigger memory and transition to post-trigger, and this pre-trigger memory now holds a history of what happens before the violation of that 2000 count ADC code. So you get a picture of what happened after the event, what happened at the event, and then 4 megabits of data showing the customer what's going on before the event of interest. So this pre-trigger memory really allows you to get a great picture of what happens before, during, and after an event of interest. And so that's the main driver for this. And 4 megabits is quite a bit. Running at max data rate, it's not a long time, but it is quite a bit of information. And below that, the 1 gigabit non-volatile post-trigger memory, and configurable threshold auto-triggering, which is what we've touched on a little bit here, is setting that threshold, which drives the transition from pre-trigger to post-trigger memory. And so that's a general outline of this device here from its core operating characteristics. There's a brief description you can read. This brochure can be pulled off of our website, so feel free to go check this out. There's a brief description here. We also have a support address. Feel free to email us at support@RisingEdgeIndustries.com for more information, and you can visit the website for more documentation as well. So this covers from a high level what the product is. It was designed to improve data acquisition in extreme mechanical environments and shock environments, and the highlights again to reiterate: in the architecture, design, and development of this, we really wanted to eliminate the need for customers to modify the product hardware in any way. We wanted finer control over gain, DC offset from a software interface, so the user doesn't have to risk damaging the product. And so all of that's implemented. The product is based entirely on a non-volatile memory system. Right now in a machined 3-part aluminum housing that's fully potted. We also didn't want customers to have to design in or actually install their own battery pack. So we have an embedded battery pack potted in the device. We have a battery control system, charge control via USB, and battery status displayed in real time in the software interface. We wanted to improve the comm link from a serial port to a very simple, painless USB plug-and-play interface. So we've finally gotten there with a ruggedized cable and interconnect from Glen. We wanted pretty much all of the interface to be cabled out if customers felt they had that need through a bulkhead. So this product can be embedded into closed systems where customers don't have access to the device and don't have access to these LEDs. We provide vias for customer wire harnessing out to a bulkhead. So we also provide a backup in case there's a physical damage to the connector. We provide a backup access to the USB interface into the logic devices here. And so really we wanted to provide as high quality and as high of reliability as we possibly could, and also as many opportunities to reasonable backup plans to allow customers to get in upon anything that goes wrong, failure, damage, to still be able to get their data out of the product, even if the product is fatally damaged. The data is very key for us, and so a lot of focus and engineering has gone into making sure customers can get that information out. It can be quite valuable, especially in shock tests and in some of these extreme environments. So we also had one of our big drivers in the embedded design and analog design was to really get the signal conditioning and control implemented in the continuous domain, not in the digital domain, so that the signal that's presented to the A to D undergoes gain, offset tuning, filtering within the analog domain to preserve information and present the maximum amount of signal content to the analog to digital converter, so the customer can get the most out of this information, get the most out of their analysis. The data files are all open CSV formats. The customer can use our software or their own software to process these. There's a time column and then 1, 2, or 4 data columns. And the software also produces CSVs in 2 forms which we'll talk about more detail. We'll have to wrap this video up shortly, but we produce 2 data files at all times in the root directory of the software. We produce a CSV as a .csv with a time column and floating point numbers, and data samples in floating point numbers representing voltage. We also produce in parallel a CSV file that contains a time column with floating point numbers and seconds, and data columns and ADC codes. And those are the codes that the analog to digital converter produces. They are not modified in any way by the internals of this product. So if the customer does want to see exactly what the A to D puts out to the memory system and what's stored, you can check that data file. It's the raw ADC codes. They do equate, because all the signal conditioning is done in the continuous domain. They do equate to what comes out of the A to D. There's no post-processing going on within the product itself. So it's a direct conversion once in the digital domain. There's no modification to the data by us. In the software analysis tool is where we do our post-processing, or allow our customers to perform computations based on what our software supports at the time, and that can be done there, but there's no type of modification to the data done in our device. The data is also written in real time to the non-volatile memory arrays, both pre-trigger and post-trigger memory arrays. And so if there is some sort of failure mode that occurs during a test, any data written to the product is in the product and is retrievable. So I think that at this point we've covered pretty much everything this product has to offer from a very high level. There'll be quite a few more videos touching on the detail, example use cases, lab testing of this device, and also going over the software interfacing. But I hope this gives you an idea of what the product is, where it came from, what kind of technology we're trying to bring to the market. We're really trying to improve these products so that customers have increased reliability, much increased performance, and much easier, or much more convenient interfaces to work with. So feel free to contact us at our support address and pull down a documentation from the website. And thanks a lot.